Alright, hello everyone. I am Professor Caudill, and today we are on vectors. Finally, something new. So hopefully this chapter is pretty fun. So let's see what it's all about. Signpost is analogous to a vector. Distance directions. Distance is a scalar quantity. So that means it can be multiplied by a constant. So you need to know both the distance and direction to get to town. Alright, so vectors are essential for physics and engineering. Many physical quantities are vectors. Displacement, that could be like an integral of a speed. So that's how much distance has been covered over time. I think velocity, we know that. ds over dt. Force, what is that? Force is mass per acceleration, something. Electromagnetic vector fields. Um, yeah, I don't have good intuition for these yet, so it's a good thing for me to learn. So vectors, scalar products are vectors, can be energy. Vector products of vectors define still other vector physical quantities such as torque. So vector products. If you don't know what vector product is, it's like v times u, and that would be like v1, v2, v3, u1, u2, u3, and I don't want to butcher this, but I think it's something like this. And you sum up those products. Vectors are components of physics in much the same way sentences are a component of literature. So if you don't know, the intro of this series of the whole school is kind of a linear algebra graphic, I would say. In introductory physics, vectors are Euclidean quantities. Geometric representations as arrow in one dimension and two dimensions. One-dimensional arrow on a two-dimensional plane or three-dimensional space. So those are called analytical vectors, I'm pretty sure. They can be added, subtracted, or multiplied. In this chapter, we will explore elements of vector algebra for applications in mechanics, in electricity, and magnetism. Sweet. Vectors operations have numerous generalizations in other branches of physics. Okay. Vector is very useful. Scalars and vectors. So what's the difference between a vector and a scalar quantity? Magnitude and direction of a vector. So what is that? I think that's the norm. Is that the norm? It's like you have a vector v times vector v. What is that? Square root of it equals the norm of vector v. That's just from memory. Might not be correct. Explain the effect of multiplying a vector quantity by a scalar. So, v1 is a vector, v1, v2, and then if you had times, let's say, a scalar, c, then that would be cv1, cv2. Okay. Describe how one-dimensional vector quantities are added or subtracted. Okay. Explain the geometric construction for the addition and subtraction of vectors in a plane. So that might be like you have your z, and you have your x, and you have your y, and you're trying to draw a vector in this three-dimensional grid. You know, how do you might be asking how you do that. All right. Many familiar physical quantities can be specified completely by giving a single number and the appropriate unit. For example, a class period lasts 50 minutes. Gas tank holds 65 liters. Distance between two posts is 100 meters. A physical quantity can be specified completely in this manner is called a scalar. Scalars are a system of number, time, mass, length, volume, temperature, energy are scalars. So scalars C could be time, mass, length, volume, temperature. What do they use? I think they use theta, like thermodynamic temperature is theta, capital theta. And energy. So those are our scalars. Time, mass, length, volume. I didn't know volume could be a scalar. Scalar quantities that have the same physical units can be added or subtracted according to usual rules of algebra. Class ends 10 minutes earlier is 40 minutes. 60 calorie serving corn, and that is 260 calories of energy. When we multiply a scalar by a number, we obtain the same quantity, but with a larger or smaller value. Yesterday we had 200 calories. Today's has 4 times. Then we have 800 calories. Two scalar quantities can be multiplied or divided to form a derived scalar quantity. Okay, that's a big term. Write that down. Key words. Derived scalar quantity. For example, if a train covers 100 kilometers per hour, it's 100 kilometers per hour. Speed is a derived scalar quantity. Okay. So, like, derived scalar quantity. So, G meters a second. So, the rescue team must know not only the distance, but the distress signal, also the direction from which the signal is coming, so they can get to its origin as quickly as possible. So, physical quantity is specified completely by a magnitude and a direction, number of units and a direction, called vector quantities. Example of vector quantities include displacement, velocity, position, force, torque. Right. Vector quantities. Displacement, velocity, position, force, torque. In the language of math, physical vector quantities are represented by vectors. So vectors you can add or subtract to multiply one by a scalar vector, but we cannot divide by a vector. I know you can build matrices from vectors, or matrices. Vectors are like a branch of matrices families, and you can divide, quote, divide matrices by multiplying one matrix by the inverse of the other. Um, so, for example, if you have AX equals B, where this is a matrix, this is a matrix, and this is a vector, you could find this by doing, I think it's a lowercase b. These are both vectors. This is a matrix. And you could, I think, do it like this. Order does matter, but these might be swapped, so possibly. It's from memory. We draw a vector from the initial point called the tail to the head. Magnitude is always a positive quantity. Tail to head. Okay. Let's examine vector algebra using graphical method. Be aware of basic terms and a qualitative understanding. Because of physical problems, we use analytic methods, which we'll see in the next section. More computationally accurate pangraphical methods. We adopt a common convention that a letter in bold type with an arrow above it is a vector, and a letter without denotes a scalar. Okay, fair enough. Suppose you tell a friend. Alright, so suppose you tell a friend you have discovered a terrific fishing hole 6 kilometers from your tent. It's unlikely your friend would be able to find it easily. Let's compute the direction. So you get two pieces of information, distance and the direction. Magnitude or direction. So I think it's interesting that the last chapter kind of talked about orders of magnitude, and now it's using magnitude in a slightly different sense. But not so different sense. So the displacement is a general term used to describe a change in position, such as a trip from the tent to the fishing hole. All right, so the displacement vector. All right. So you could say this vector is equal to A to B. Since the magnitude of the vector is its length, it's a positive number. So D is equivalent to absolute value. To solve a vector problem graphically, we need to draw the vector D to scale. So if we use 1 unit of distance kilometer, all right. Magnitude 6 kilometers. All right, so Suppose your friend walks from campsite A to B. Go in A to B. And then walks back. Okay. The magnitude of the displacement vector. Okay, so you're saying magnitude is okay, so call these D. So D A B DB DAB equals DBA. Vector AB is not equal because these two vectors have different directions. Okay. Magnitude equal direction not equal. Two 2.3. So in this figure, BA would be represented as a vector with origin at point B, point southwest, which is opposite. We say BA is anti-parallel to AB. Okay, I haven't seen that notation before. DAB is anti-parallel to DBA. Two vectors have identical directions are said to be parallel vectors. They're parallel to each other. Equal. So A is B if and only if all right, so parallel. These are parallel. These are parallel. These are anti-parallel. These are anti-parallel. They're the same size, same magnitude and direction, they're equal. Okay, and then orthogonal. So I think E is a little interesting in it. I'm glad they notated that doesn't have to be the endpoints don't have to be connected to the right angle. I think that's kind of neat. All right, so I think so. These are not equal because their magnitudes are not equal. I think they're using the capital letter here for magnitude, right? So A and B are not parallel. There's a lot of information here. So yeah, let's check our understanding. So Alice and Bob, given the information about their velocity vectors, use some following to indicate whether their velocity vectors are equal or not. So A, say A is Alice's velocity vector, and A moves 6 north. So A is, say she starts at the origin and she goes so XY, Alice goes from the origin to 6. So analytically, Alice is here. 6. Okay. Bob moves west at 6 knots. Bob goes west 6. So he's going to have 0y -6. Okay. Alice then moves A1 plus moves west 6 knots. Okay, so Alice is going to move west 6. Okay, and Bob moves west 3 knots. All right, northwest, north, west, and then west, west. Okay. All right, and then Alice moves northeast 6 knots. Okay, that's a tough one. Northeast 6 knots. So what is northeast 6 knots? That's 3 north. So 3y, 3x. I think it would be 6, 6. Okay. And then Bob. Bob moves 6 southwest at 6 knots. Southwest. Okay. Okay, and then lastly, Alice moves northeast 2 knots to 2. And Bob moves northeast 2 knots. Okay, so what's happening here? So this is our X, this is our Y. So Alice is going to go to 6. So this is A1. And then Alice is going to go -6. Right here. And then Alice is going to go +6, +6. So +6, +6. A3. So Alice is going in a little zigzag. And then Alice goes +2, +2. 1, 2. It's going to say 1, 2. A4. Okay, so that's the path Alice went. Now, let me change the color. Can I change the color? Okay. Uh, okay. So Bob. It's going in a different direction. Um, 1, 2, 3, 4, 5, 6. Okay, so Bob is going here. Then Bob is going to left 3. And then Bob is going 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Bob's going way over here. And then he's going +2, +2, so he's going to actually backtrack to here. So this is where Bob ends up. This is where Alice ends up. Alright, so vectors can be multiplied by a scalar, added to other vectors, or subtracted from other vectors. We can illustrate these concepts using the fishing tramp example. So, stopping at a rest point C. Going back for the tackle box. And finishing up at the fishing pond. So, A to C, A to B, A to D, okay. It's not the most clear picture, but I guess it helps a little bit. So suppose your friend parts from campsite. All right. Suppose your friend departs from point A and walks to point B. So 3/4 the distance from A to B. What is his displacement vector? Okay. So I think we're looking at example 1, which has a magnitude of 6 kilometers in a direction northeast. If he walks only 3/4 of the fraction, maintaining his direction, point C must be 3/4 or 4.5 kilometers. So displacement vector of AC is if all right. So basically D AC is 3/4 D AB. Now this is our first vector equation. In a vector equation, both sides of the equation are vectors. Okay, I might not have seen that before. I mean, this seems important. Both sides of the equation are vectors. Previous example is a example of a vector multiplied by a scalar. alpha is 75, and the result DAC is a new vector with the direction parallel direction. And vector A is multiplied by a positive scalar alpha. The result is a new vector B that is parallel to A. Okay. Magnitude B. So if you want the magnitude, take the absolute value of alpha times the magnitude of A. So magnitude is how many units or how long the vector is. Here's scalar equation. Both sides equation are numbers. So that's probably what you might recognize from elementary school, K through 12. Alpha is 2, the new vector has a length b equals 2a. A is -2, the new vector c equals 2a equals 3 units. Okay. Seems to be making sense so far. A 1.5, B equals 2a equals 3. Vector B equals 2 times the vector A. C, if you want to go the other direction, take the negative of it. A is 1.5, B is slightly longer, R is A plus B. So that's kind of what I did in there over here earlier. A 1.5, B slightly longer, A going this way, and then B is coming this way. A plus B from the opposite direction, so A minus B. The displacement is the absolute value of that. Okay. Seems to be going good so far, I think. Now, suppose your fishing buddy departs from point A, walking in the direction to B. At rest point C is this. Starting at point C, walks southwest, which means displacement C, it's anti-parallels. Its magnitude dCd is this. So his second displacement vector is dCd. Vector sum of the two displacements vectors. Vector sum of two or more vectors is called the resultant vector. When the vectors on the right hand side are known, we find the resultant AD as follows. AD is AC plus CD. That's 3/4. So vector going a vector this long multiplied by this constant this way plus vector going the opposite way is scalars a minus b times AB. So you're breaking this down into just a scalar times AB. dB is the difference of two vectors. Difference of two vectors is nothing more than a vector sum of two vectors, because second vector seems to be making sense. Like, I think this will be more interesting when we do kind of independent examples on our own. When A and B lie on a line, and their difference both lie in the same direction. Alright, so when a vector is antiparallel to B, draw them along one line in either head to tail fashion. In general, in one dimension, as well as in higher dimensions, as in a planar space, we can add any number of vectors and do so in any order, because addition is commutative. So A plus C plus B equals B plus A plus C. In associative, so multiplication is distributive, so A1, A2, when adding many vectors in one dimension, it's convenient to use the concept of a unit vector. Symbol with a hat, so U hat, U hat, U hat, U hat, U hat. Okay. U hat unit vector. Magnitude of 1. Magnitude of 1, so absolute value of U hat equals 1 equals U. Okay. Only role unit vector is a specific direction. Then southwestern direction is given by unit vector negative U. In this way, the displacement of 6 kilometers southwest is expressed by U hat. Okay. Example. Long measuring stick rests against a wall. Okay, so we have a wall. And a long measuring stick rests against it. So here's our measuring stick. Alright. A ladybug lands on this and crawls up. So first, okay, so we're gonna say where it lands. It's gonna be that's where our graph's gonna start. So we're gonna introduce a unit vector. So it's gonna have a magnitude of 1, direction, so I think it would just be 1, 1 for northeast. Up 1, right 1, up 1, right 1, up 1, right 1. Does that make sense? So the ladybug goes for it first walks 50 minutes towards the floor. Okay. So the ladybug lands in the middle. Okay. So it first walks 50 minutes towards the floor. So it's going this way towards the floor from the middle. So let's say I hat is towards the floor. So that would be down 1, left 1. No, left 1, down 1, X, Y. Okay, so let's say it lands at A. It's going to B. So A, B, we're going to say this is its first move. So the first move is going to be $15 I hat. Okay. And then it walks. So now we need a towards the wall. So we're going to say J hat towards the wall will be okay. Let me make sure I have these numbers right. So unit vector is going up. So 15 centimeters towards the floor. So this is to the floor. Okay. So if it's going walks 15 meters towards the wall. Now it's not going straight it's not going straight left because remember it's resting against the wall, so it's at an angle. So when it says walk 56 centimeters towards the wall, it's actually going northeast. So it's going to be a U hat. So it's going to be 56 centimeters times U hat, or it's 56 meters in the northeast direction. Okay, so I'm sorry, that's actually going to be move 2. It's going to be move 1. It's going to be 56 U hat times plus move 1. So it's going to go from the origin, which is here. It's going to go this direction, negative 15, down 15, left 15. Okay, and then from B, it's going to go up. From this position, which is M1, we're going to add 56 U, which is in this direction. Okay. Then after a brief stop, it continues 25 centimeters towards the floor. So M3 is going to be 25 towards the floor, I hat, plus M2. Okay, and then crawls 19 centimeters towards the wall. So this is the wall. You are not tracking. Okay, so this is the ladder. Okay, so M4 is going to be 19 towards the wall, so that's going to be I. No, that's going to be U hat. 19 in the direction of U, going towards the wall, plus our last position. Find the vector of its total displacement. Okay, so that's a tough one. Total displacement. So the displacement of MU is going to be absolute value 19 U hat plus 25 I hat plus 56 U hat plus 15 I hat. So that's going to be 20, 34, no. 19 plus 56. 55, 65, 65, 75 U. 40 I. So U is going to be positive, so it's going to be 75. 35 centimeters. Let's see if I got it right. 32 centimeters. I was close. Maybe I messed up some algebra somewhere. 56 plus 9, 65, 75. Plus that. Okay, well, let's check our numbers. 15, 15, so I see what they did. They did this a little smarter. They just did negative u hat equals negative I, negative 1. So we should have done this, but I think we're on the right track for the most part. So we have 19, 25, 3 centimeters. Okay, so I missed the 3 centimeters somewhere. Yeah, so I definitely missed this part. So that's why we're off by 3. So I think we nailed this one. In this calculation, we used the distributive law. Final position would be 100 minus 32. All right, I think that's a good place to stop. We'll pick up on 2.2 next time. So thank you guys for hanging out. We'll see you next time.